Good afternoon. I have kept the concept of this work in mind for years, but took action only after submitting the abstract. After 4 months of research, I had to put a part of the title in brackets and become uncertain about the idea. Let me start with an introduction. The gravitational fields of planetary bodies are represented by 2D spectra known as spherical harmonic coefficients. Assume the spectrum is isotropic, in other words, that the power of the coefficients depends only on the degree. It then makes sense to examine the RMS of the coefficients and determine its statistical fit as illustrated in the figures. The simpler 1D measures are helpful, for example, in error propagation studies or as constraints in least squares. The literature, however, does not adequately address vertical changes of these spectral characteristics close to topography. In this talk, we analyze gravitational fields of the 7 listed planetary bodies. We calculate spherical harmonic coefficients using our forward modeling approach at the three spheres illustrated in the figure. The red sphere passes through the topographic minimum, the blue one is the best fit, and the green sphere envelopes the body at its topographic maximum. We assume homogeneous compositions and detailed geometries as provided by the respective satellite missions. The anticipated output is a set of 7 radially dependent Kaulas rules between the red and the green spheres, justified by 2D isotropic spectra. We restrict ourselves to only 2 planetary bodies. The first is the Moon, whose low flattening perfectly suits the spherical approximation. We calculated the spherical harmonic coefficients at the 3 spheres up to degree 2519. The forward modeled fields were based on a constant density of 2550 kg per meter cubed, and the illustrated LOLA topography with a resolution of 1/14 arc degrees. We now examine 2 spectral characteristics, firstly at the enveloping sphere. The magnitude of the coefficients is shown on the left. It decreases with degree column-wise, while we cannot see any trends with order row-wise. The neat 1D measure on the right is the RMS of the coefficients, and it reveals an asymptotic decrease as the degree increases. At the best fitting sphere, the 2D spectrum on the left keeps a similar pattern, but its values are higher. The stronger power is clearly seen from the blue 1D spectrum depicted in the right figure. At the lowest sphere, the magnitude of the coefficients drops again with degree, but we can identify the smallest magnitudes in the sectorials and higher powers in the tesserals and zonals. The corresponding red RMS of the coefficients on the right is almost identical to the green one at the enveloping sphere. Similar findings are also valid for Mars, though the 2D spectra there appear to be even more anisotropic. The second planetary body is the oblate asteroid Vesta. We can imagine its spheroidal shape from the illustrated topography. We computed the spherical harmonic coefficients at the 3 spheres up to degree 719. We utilized the terrain model from the Dawn satellite mission with a sampling interval of 0.25 arc degrees and a constant density of 3,513 kg per meter cubed. We now investigate the two spectral characteristics, starting again from the enveloping sphere. The magnitude of the coefficients on the left decreases with degree, but we can identify a systematic pattern as the order changes. The RMS of the coefficients in the right figure decreases asymptotically and is completely blind to any small anisotropies. At the best fitting sphere, the coefficient's power has two distinct features. Firstly, it decreases with degree for the tesserals and zonals. Secondly, we can see a sudden drop towards sectorials. As for the Moon, the blue 1D spectrum on the right is stronger than its green counterpart at the enveloping sphere. The anisotropic nature is even more pronounced at the lowest sphere. Here we can observe the loss of power mainly as the order increases. The corresponding red 1D spectrum on the right is close to its green counterpart at the enveloping sphere, and it asymptotically decreases as its values come from the zonal coefficients. Similar findings also apply to Bennu, Ceres, Eros, and Ryugu. I now go to the conclusions. In this talk, we analyzed gravitational fields of 7 planetary bodies close to their topographies. We demonstrated vertical changes of the spectral characteristics and the strongest power at the best fitting spheres. We showed that the 2D spectra may be anisotropic, in particular for the flattened planetary bodies. So far, the anisotropic traits have discouraged me from completing the initial objective, which was to find 7 radially dependent Caulas rules. That is all from my side. Thank you for your attention.